Okay then, good morning everybody. I'm very happy to see that the room is full again. So you are fresh and excited about our keynote speaker today, this morning. And yeah, sometimes, I mean, it's very easy to actually find the best person for a presentation in your institute. And that is actually making me very happy that Vedran was willing to give the presentation today. He's a colleague at the Leiden Institute of Advanced Computer Science and obviously also affiliated with the Institute of Physics. And he's kind of building the bridge between the two, actually being very knowledgeable in both fields and doing quantum machine learning, quantum computing, quantum optimization, and stuff like that. And I think this is so interesting for our field that we unanimously decided that we would want a quantum computing keynote speaker. And he's really the best person, in my opinion, to give this presentation today. So for his background, got his PhD in 2013, 2012 at Watts University, right? And then we were very lucky to actually get you to LIACS somewhere around 2018, if I remember correctly. Yeah. And now he's a professor in quantum computing and leading the AQUA group, Applied Quantum Algorithms group, which is about 40 people, right? So that's really a significant activity here at Leiden. Vedran, the floor is yours, and we are very much looking forward to your presentation.
Thank you so much, Thomas, and thank you and Anna and Eleni for the very kind invitation. So I have to confess, I was really excited when I was invited to give this talk. It's always an interesting challenge to talk to a community that you're not a part of, and to get to meet new people and new ways of thinking. And they asked me to say something about optimization and quantum computing. And I said, yes, of course, absolutely. And then come this Sunday, I realized that I should say something. And then I realized that I'm actually not an expert on optimization. It's something that I encounter in the type of quantum computing I do. I actually work in quantum machine learning. And so I was thinking what I'm going to do. Thomas would like me to say something about optimization. So maybe I talk about quantum machine learning and then say something about optimization. Everybody's happy. And then I check with Anna and I realize that indeed this is not an interdisciplinary audience. So can somebody tell me, I want to break the fourth wall a little bit. Is anybody actually secretly an expert on quantum computing in the audience? There are some experts, so I will be very grateful when they start correcting me, and please do that as we go ahead. So the second thing was like, I should explain quantum computing, right? If this is not really where you're from. So then I could spend an hour doing that and tell you nothing about the research. So it's a conundrum. So I wrote an enthusiastic abstract saying, I'm going to tell you about machine learning, optimization, quantum computing, and then I prepared the slides. I looked at it, so okay, this is 3-hour talk. Then I checked the timeline, doesn't fit. So then I had to sacrifice something. So I'm going to tell you about the things I know the least about, honestly, optimization. But hopefully know some things that maybe you're not aware of and maybe you find it interesting. And I will be deeply grateful if you interrupt me and ask me questions and we fail to get to the end because we engage in a discussion. But it will also be okay if I just finish and you heard something and we move along. So yeah, as I said, I will certainly not be talking about evolutionary algorithms. So that's something that has been overlapping with quantum computing to some extent, but I don't know much about that. I will be talking more generally about optimization, and this is the place where, in fact, evolutionary algorithms and quantum computing somehow do touch, at least in the sense of inspiration, right? Because both quantum computing and evolutionary algorithms are inspired by nature, different parts of nature, so to say. And as I'll try to argue in the beginning of the talk, for evolutionary algorithms, you know this. For quantum computing, it's also true that in a way, it solves an optimization problem. And Thomas would say very correctly, everything is optimization anyway, so this is not a surprise, but it's a little bit more specific, and I'll try to convince you of that in the beginning of the talk. But let's start with something that, even though you don't consider yourselves experts in quantum computing, I'm sure you know the background of quantum computing, where it comes from and what part of nature we're talking about. So somehow it goes back to, let's say, even before the 70s, but certainly around the 70s, people started thinking more about this, is how do you simulate physics on a computer, right? So a typical, what do I mean by this? Suppose we're talking about materials. So this is some kind of a lattice of atoms. These colors are atoms of different species, and maybe I know where they are in space. It's a solid, right? And I give you this information and tell you it's a big thing. These are rubidium atoms. I have no clue, silver atoms. I don't know anything about materials. and you make it really, really big, so no Avogadro number here, here, and here, so 10 to the 23 of things. If I were to plug in probes here and measure resistance, will I see zero resistance? Is it a superconductor? You might be aware that this is a very popular question, right? A very important question to try to predict superconductors, right? So that's one question that you might want to answer on a computer, right? You could simulate the material, figure out whether it's compute the resistance, right? Here's another thing, so you might not see exactly what this is, so I zoomed it up. This is an actual thing, this is an optical table. You shoot laser beams here. You shoot them through optical fiber, it goes around, goes to some optical element, something happens, and somewhere, in fact, not here, because this is for cold atoms, not photonics, but if it was for photonics, there would be something called photon detector somewhere, which we say click. I saw a photon, right? So I give you the description of this table here, and I tell you I shoot a laser beam here, and I ask you, tell me which one of these detectors click, right? So these look like very different questions, but it's quantum physics. So on some abstract enough level, it's sort of the same type of a question. And it turns out that we've been thinking about this, much smarter people than any we that includes me, have been thinking about it. And the best calculation methods that we have scale exponentially with sort of an inherent size of the description, like the number of atoms I'm going to plug in here, or number of optical fibers that are involved in this experiment, right? And this is like, it's not like, yeah, we thought about it a little bit, we don't know how to do it better than, no. People have seriously thought about it, and there's very good reason to believe this is really fundamental, that you cannot do in general better than exponential in the number of systems, right? Not always, but in general, it requires this much time. So this is the type of thing you want to do. And then the next thing I would like to point out is that these are kind of different, right? I mean, this is a material. This is something we cooked up in a lab, right? This is what you call an experiment. This we wouldn't call an experiment. This is an artifact. People have made it. It's controlled. I can make it do something else, right? I can turn an optical element. I can cut a fiber. Now it's doing something else, but it's still in my lab. I can still shoot lasers and make it click, right? And in fact, I can modulate it in such a way to start looking like some other experiments. And it turns out that, in fact, if I build it big enough and complicated enough, I can make it to look such that if detector A clicks, then this is a superconductor. And if detector B clicks, this is not a superconductor. Because the terminology will be the effective physics of the two systems is the same. It doesn't really mean what this, I think you understand. I hope you understand what I'm trying to depict here. And this is essentially the idea behind quantum computers, right? So quantum computers are, in the broadest sense, highly controlled quantum experiments that can be made to simulate a family of other experiments or physical natural systems, or perhaps all physical systems, because we have a notion of universality, both in the sense of simulation and, as I'll say in a second, in the sense of computation. So this is 1981. Feynman and Yuri Manin were thinking about this, and in fact, their main point was that if you want to simulate a physical system of this kind, you can only do it with another physical system of the same species, in a sense, a truly quantum system, right? And because of this inherent exponential scaling, if you try to do it with a classical system. That's the birth of quantum computing. And now this is sort of very physics, but then you think about it a little bit more, and comes David Deutsch and defines a quantum Turing machine, and already Feynman set the stage for so-called circuits. And then you can start thinking about computation in a more abstract way, more similar to what people have been doing in theoretical computer science, since Turing and onwards. So you have classical circuits, which have bits and have logical gates, and ultimately everything we do in there boils down to this. Similarly, in the quantum world, we have things which we call qubits, which are pretty much like bits. They can be in 0, 1, and in some sense, some things which are not 0, 1, something which looks like probabilistic mixtures, but they're a bit more complicated than that. And we have gates which manipulate what the state of the register is, right? And I will say the first technical thing, which I also suspect many of you know, and there's going to be 2 or 3 technical things in talk in total, that the state of the system. So if I ask what's the state here, the answer is a bit string, right? So I'm living in F2 to some power, right? I'm living in the state of bit strings, always. Here, the state is a linear combination of bit strings. It's a formal linear combination of all possible configurations of bit strings that I have, right? So here's a bit of math. So if you're not from quantum, but you've done linear algebra at any point, you will see some formal sums with coefficients, and these things are, you can think of this as canonical basis vectors in a 2 to the n dimensional space. right? And now I have these coefficients, they're complex, it's a complex valued vector space. There's a normalization constraint on this. It's like probabilities sum up to 1, and these things sum up to 1 when I take norm squared. It doesn't matter that they're in a sphere, right? And then to make it fancy, you make it quantum mechanical, that your vectors are no longer bold-faced or have an arrow above, but you put this weird bracket here, which we call the ket. It's called the Dirac notation, but it's the same thing, right? And if you're more computationally oriented, then it's a numerical vector, right? The dimension of which is 2 to the n. Each one of these things are complex numbers. That's a quantum state, and we don't know how to represent it more succinctly. And it does correspond up to maybe 1 or 2 degrees of freedom to whole elements of physical reality. Meaning that if I change one of these guys, I actually have something different in the lab. Like, so there's no redundancy. It might be the case that you cannot practically reach all of them in finite time, or, well, in polynomial time, but that's a different story. So far, so good? That's why it's hard to simulate quantum computers. You have to store 2 to the n things. You can avoid it. Quantum computing turns out to be in p-space, but then you pay price in extra compute time, which is exponential anyway. Good. So we have a register, we have an initial state, we apply gates. We have things which look like classical logic gates, which split the bit or flip a bit condition and state another one, like an AND. But there's also a continuum of other things. Like, in fact, these quantum gates are more like rotations. And it turns out if you can rotate individual qubits and pairs of qubits, so this is like a 4-dimensional complex rotation, that's all you need to realize any rotation of any dimension. That's sort of a universality result. So we think of them, or for the purpose of this talk, I want to think of them as being things which are parameterized by, let's say, one real number. That's going to be good enough for me. And you can think of it as an angle. That's why I call it theta. Okay? So these are circuits that has gates and prepare some quantum state. That's all I need for quantum computing right now. I don't want to belabor the topic. But I want to tell you where we got in building them, right? Because this is kind of, I understand you're theoreticians, so maybe you don't care that much. Admirable. Some people do. What we need is we need qubits of high quality. We need the capacity to implement gates. We need a way to measure them. I don't want to talk about measurements at all. I have to tell you that no matter how well we do, eventually large errors in our gates and qubits are going to be unavoidable. Like with 10 to the minus 4, 10 to the minus 5, you're going to make a mistake in what you do. This is sort of for fundamental reasons. If you wish, you can ask me later about it, what I mean by that. When I say large, I mean, this is in compared to classical logic. Like classical logic, I actually checked it a little bit. I mean, depending on how you look at it, I mean, the error rates in CPUs are like 10 to the minus 15. So maybe 10 orders of magnitude better than what we can get quantumly. And this implies that we really have to have fault tolerance error correction on the machine. You cannot really do larger computations than 10 to the 4, so not that big, without having to resort to error correction, right? And this is expensive. This costs physical qubits for logical qubits and so on. So where are we with this? Well, now we have many ways to build a quantum computer, or towards building a quantum computer, in various types of systems. In pure photonics, when you manipulate states of light, in cold atoms, in so-called superconducting qubits, which are modifications of which are so-called electrical circuits, which are very, very cold. In so-called NV centers, these are imperfections in diamonds. All things when you kind of know that the single quantum degree of freedom is somewhere where you can make it a qubit, right? And in many platforms, we have these high-quality gates, high-quality qubits, and specifically in superconducting and neutral atom architectures, really in the last 5 years, there has been staggering progress. Like, you will ask me eventually, but how far are we from quantum computer? I'll tell you in a second. But locally, if you look locally, it has been more than we expected if we knew what we're talking about. Let's put it this way. So this is just a couple of papers. I mean, slides are going to be, I can send them to you. More for reference. I don't want to talk about this thing, but I mean, IBM is not totally crazy when they talk about having, you know, a couple of thousand qubits maybe in a year from now, and they're already at thousands. In Misha Lukin's lab in Harvard, they're already controlling 3,000 qubits, not universally, but very, very precisely. So I mean, the story is orders of magnitude above where it was just 5 years ago, let's say. But this is still very far, right? Very far from the types of things you may think about, you may want to do. I don't know, for now, I don't know. I suspect some of you are old enough to know what a Commodore 64 is. It was the first computer I was not really allowed to play with yet. 64 kilobytes of memory, not much, right? Not much you can do. I mean, this is mind-bogglingly far from where we are right now. Right now, we can think about thousands of physical qubits, those with errors. And maybe if we have really, really good error correcting codes, then we can get maybe 10 logical qubits out of that. This you can compute on a calculator almost by hand, whatever you're doing. So it's not yet what we want. And it's very hard to scale it up. And how hard? Harder than putting a person on the moon. Much harder than that. Let's just put in some context. And the bottom line of this is that either we have to kind of give up on error correction completely, in which case we cannot really run the algorithms we know, or we don't and we kind of use very few qubits. And then again, we cannot really run the algorithms we know because all of them need many, many more qubits, right? So huge progress, but still not where we want to be. But at the same time, people were really thinking about what to do with these devices that we have. And they figure out that already they're doing stuff that you cannot do classically. So this is something you also may have heard about. It's a contentious title. It's a contentious term. It's called quantum supremacy. Some people really don't like the term. I'm sticking to it in a very technical sense. You can again ask me later how we distinguish supremacy from advantage, from primacy, and there's a bunch of species of advantage. For me, this is simply empirical demonstration of a computation that is provably something that a classic computer cannot do at scale. Again, query me later if you wish. And this has been achieved. This is, I think, by now pretty much uncontroversial. The quantum computers that we have can do stuff that you cannot compute classically. Good news. Bad news, nobody cares about that stuff. They're utterly useless computations to the point that you might wonder, well, are they trying to make it useless? They're not. It's just easier to prove stuff for weird things. So the intuition is there is some power in it, right? We're just not clever enough to use it. So it's untamed. Maybe there is nothing there that's actually useful. Maybe it's untamable. We don't know. But for many of us, it's like somebody gives us this magical hammer. And these are all the problems that we want to solve, which are not well suited for a hammer. And that's the situation. It's our quest for the killer app. Okay. But let's still try to talk about prospective actual nails for a magical hammer. Okay. So let's talk about quantum computing and optimization. I realize I need to pick up the pace a little bit. So let me try to convince you that quantum computing is in fact optimization, that it's not obvious that it's not good for optimization. But before I do that, small disclaimer, I will tell you one way of thinking about quantum computing optimization. It is not the only one. It is probably not the most promising one either. It is just one which is a very nice synergy between classical and quantum computing that I would like to tell you about. But otherwise, please ask me. There's a bunch of other ways of doing it, both continuous, discrete, and so on. It's a small thing. Yeah. So quantum computing is optimization in a way. And the first way I want to argue is from complexity theory. That there's a very simple optimization problem. It's a continuous optimization problem, which very finely captures what quantum computers can and cannot do. Okay. And this is the problem. I'm going to give it in pure physics, but the terminology is going to smell like physics because it is. So the input to the problem is a large matrix. It's a Hermitian, if it's real symmetric matrix of dimension 2 to the n, with times 2 to the n, where n is the parameter that I'm actually scaling. And of course, I mean, I cannot give you an exponential large object in polynomial time, and I'm interested in things I can do in polynomial time. So I give it to you succinctly. I give you a short description of a big object. Like the simplest way to think about it, if you know what Kronecker product on matrices is, it's a way you multiply two matrices, but the dimensions multiply. So it rapidly grows. You give me n matrices, but it's actually representing a much larger object. So this is how I give you the matrix. And your job is to estimate, for now, its smallest eigenvalue. So solve this particular optimization problem. Sounds like a very natural thing to do. If it was not exponentially large, this is easy. You do it in what, quadratic time or even less. But here you're dead because the matrix is exponentially large. Or sometimes we care about not the properties of the eigenvalues, but the properties of the eigenvectors. So I ask you something about the eigenvector which has the minimal eigenvalue, right? For instance, we know an eigenvector is the state is a 2 to the n dimensional vector. Sum up first half of the elements, norm squared. That turns out to be a very, very natural question from a physics standpoint. I think also in math you can show that these things are very, very interesting. So I'm going to call this the ground state or the ground energy problem, because these matrices are going to become Hamiltonians, descriptions of the physical system which have energy levels, and we don't know what's the smallest energy. And it's not one, it's a forest of problems that are closely connected, okay? And now I want to tell you what it does to complexity theory. So this is I'm just going to talk about decision problems, and I'm sure you've seen diagrams like this before. So P-space, suspect you know, P, BPP, and NP you know. BQP is the stuff you can decide on a quantum computer in polynomial time with bounded error. QMA, that's the quantum analog of NP. Turns out there's no good way to define QNP. You can ask me later why. But the closest thing is quantum Merlin-Arthur. So the Merlin-Arthur, which is sort of the randomized NP class, this has a quantum analog, which is natural. So that's this class. So these ground state problems, the eigenvalue problems that I mentioned, turns out to really capture everything. So QMA is the easiest one. If I'm asked to estimate the eigenvalue to polynomial precision, decision variant of that problem, that's QMA complete. That's complete for that, completely captures it, right? Up to polynomial reductions. If I'm interested in exponential precision, this was called precise QMA because you want to be super precise. Turns out that's equal to P-space. So this captures polynomial space, and all of quantum computing is certainly sitting inside. And if you take this poly-precise problem, but you add a little bit more extra information, something which we call a guiding state or an adiabatic path, we'll talk about this in a second, then it starts capturing BQP exactly. It becomes BQP complete, okay? Note, this is not super elegant. You would here maybe I'm failing to convince you that it's really the natural problem, but this is similar how, I don't know how you feel about it, but like local optimization feels like it should be P complete to me, or BPP complete if that such a thing were to exist, but it's really not. You need to add some stuff to make it. Similarly here, you have to add some stuff. There is an optimization problem which is BQP complete. It's fully quantum. It doesn't have a classical analog, but it would take too much to go into it. But I give you a reference here in case you're interested. This abstract mumbo jumbo does have immediate consequences. Consequence one, there must exist optimization problems where quantum computers are exponentially faster than classical computers unless BQP and BPP are exactly equal. So if we at the start agree that there's a difference between these classes, already because of these reasons, this completeness, it implies that there's going to be a separation in runtimes, an exponential one. So we know that they can do something better. Whether it's interesting or not, it's a different question. Now, I didn't tell you this, but if the matrix M that is specified in my problem is actually diagonal, so it's a real value diagonal matrix, then it turns out you're fully capturing NP. That's an NP complete problem, the decision version. So if I'm interested in the intersection between these things and NP, still everything survives, and turns out you can prove existence of NP optimization problems where quantum computers are exponentially faster than classical computers, unless some funky things happen in complexity theory. So this we know as well. And you can do even a little bit better. You can invoke PCP theorem type results and prove that it also holds for approximation. So there are problems where classical computers cannot even approximate solution to constant relative error, but quantum computers can get it exactly to whatever precision you want efficiently. Right? So I don't want to belabor this too much because it turns out that these problems that separate classical and quantum are not interesting. They're very artificial. You construct them, but they're not directly useful. But at least they establish that one, quantum and optimization do have a connection. Quantum does optimize something, and two, we're not crazy to try to optimize something on a quantum computer, right? And expect improvement over classical computers. Yeah. So now I'm going to switch gears a little bit. This was one argumentation about the connection between optimization, which went through complexity theory and specification of problems. But now I want to look at it from a slightly different perspective, not focusing on the problem, but on the method, on the algorithm itself. Because I mentioned it's a Hamiltonian, energy levels, and so on. I mean, this exists in the classical world and has deeply inspired computer science and specifically optimization as well. In statistical mechanics, look, M can be a classical Hamiltonian, so that's an energy function which assigns an energy to configuration, and you can try to minimize it by doing sort of a random walk and certain updates, and voila, that's Metropolis-Hastings algorithm, right? And it's the foundations of all of simulated annealing and things like this, which are some of the more powerful optimization techniques that we still use, right? So this is in the classical world. So you heat up the system, you reduce the temperature, finding a local minimum or global minimum if you're slow enough and lucky enough. The parameter you're tuning is temperature. The quantum analog of this would not be tuning the temperature. Typically, that's not the right thing to think about, but some other parameter they'll define. And then we start talking about the so-called adiabatic method. So this is like this thermal thing, but the parameter is not temperature, but something else. You're changing the problem a little bit from an easy to a hard case and hoping for the best. Or if you do it very, very precisely, then you get the best. So let me, I don't know, is anybody familiar with quantum annealing, or have you heard anything about adiabatic? Okay. A little bit, so I hope I don't lose you completely, but never mind, even if I do, I'll remind you in a second what we're doing and why we're talking about it. So now this is again physics. So I said that this matrix M, or the Hamiltonian H, it's some kind of a description of the energy of the system. You can use it to derive equations of motion to figure out what's happening out of it in the system. But in particular, if I build a system, it has a Hamiltonian, and this thing has a ground energy and has a ground state. And in principle, if I very slowly cool down the system, I will end up in the ground state. Okay. And I can cook, and what I'm really interested in is properties of ground state. That's the optimization problem I'm solving, right? So now if I take the system and I shoot a laser beam at it, and I said that we shoot laser beams all the time, now it's a different Hamiltonian, it's a different system. Now I cannot do this here, but if I were to, diminish the power of the laser, I'm changing the Hamiltonian. So I start with a system which is controllable in the sense that I can make it to be like the target Hamiltonian, but also like some easy Hamiltonian for which I know the ground state. And I interpolate in between. I switch on the laser field, making it look like the target until the target is dominating. If I do it, there's something called the adiabatic theorem, which tells you that if I start in ground state of the initial system, and I tune it slowly enough, there I'm telling you how slowly, you're guaranteed to end up in the ground state of the target system. Doesn't look like computing that we typically do, but it's something you can do in a lab. You can define it, you can formalize it. So we're not kind of cooling the system, we're actually changing the energy landscape. It's starting in a minimum, which is eventually going to end up being the global minimum. If you do it slowly enough, it doesn't hop out. That's what's happening. And there's some time associated to how quickly I'm allowed to do this, and this governs the complexity of the entire thing. It's a model of computation, very different than circuits, very strange, takes a little bit of time to get adapted to. But it turns out it is equivalent to quantum circuits. It is fully capturing what quantum computers do in a very operative sense, that if you give me a quantum circuit, I can concoct a machine of this kind, which if I do this process in polynomial time, I will get my answer, whatever the answer of the circuit was. And conversely, if you define an adiabatic process like this, I can construct a circuit which takes this state an input and produces this state an output. This is some physics, but now I'm going to turn it into an algorithm, right? So this is what physics does. It gives us a way to go from a physical solution to a problem to an algorithmic solution to a problem where, in fact, there's a bunch of gates. These gates here that I'm applying, they depend on this initial and the final Hamiltonian, and also the time I want to run this for. So there's some parameters here which depend on this time. And when I compute these parameters, depending on the gap, I didn't talk about it, some property of this annealing process, I'm guaranteed to get the correct output out. Okay, so there's some parameters, the gates are kind of defined by the problem. And I'm going to slowly move it, but now as circuits. Like it looks very similar. Time goes from left to right. Must be the same thing, right? It's true in this case. So it's a circuit-based algorithm for preparing ground or low energy states. Now, I've been talking a lot about various things, so let me just remind you what we were doing. Recall, I was solving an optimization problem. An input is a large matrix, which eventually started calling the Hamiltonian. And what we're doing right now, we're trying to prepare a quantum state. Recall that just a large vector, which is the ground state. In other words, satisfies this. It minimizes this inner product, right? This finds the smallest eigenvalue. Now, why am I doing that? I don't get the vector out. I don't get the entries of the vector. I end up with a physical system whose mathematical representation is the solution, but I cannot read it out. It's just there. What I can do is measure. Now, measurements are destructive things, they change the system and so on, but it just so happens that this quantity here I actually can measure. I'm going to measure the system a bunch of times, and I'll get an estimate of this quantity, and I'll return to this in a second. Okay. So if I did manage to prepare the ground state, I can measure the smallest eigenvalue, which was my problem. Okay. Yeah. In the case of combinatorial optimization, where M is diagonal, this measurement is the most straightforward thing. You kind of observe the system, whatever that means, and you see a bit string. And which bit string you see depends on the underlying quantum state in some way. It's a randomized process, okay? And we're going to repeat this a bunch of times, average the eigenvalues with the frequencies, and voila, you have your solution. So adiabatic theory gave us a viable quantum algorithm, which if I tune the parameters right, which I can in principle compute from these properties here, I will get the correct state, which I measure, and I solve my combinatorial optimization problem. If I knew this gap here, just so happens computing this gap is exactly Sharpie hard, so it's even worse than whatever we're trying to do. But if I know an upper bound, I can still make it work, right? So and sometimes you have an idea for an upper bound. Or sometimes you might say, well, what if I don't care about the guarantees and I'm doing it faster? Maybe it works out, and then you invent heuristic algorithms. But what's important here that I want to go to now I have an exact algorithm which has these parameters, and gates, and parameters I should compute. I'm not sure what they are, but maybe I don't need to know them. What do I mean by this? Well, suppose I give you wrong parameters. You prepare the quantum state, you measure the energy. I'm trying to find the smallest energy. No state will have energy lower than the thing I'm looking for. So I'll find something larger. Then you take some other set of parameters, you get some other number. Whatever number I get, I'm going to get something which is larger, or maybe improved or not improved to where I was, but it's certainly never going to violate the actual true solution. So I'm always finding an upper bound. This is something which we call the variational principle in this context. It tells us that if we optimize over the parameters and we find the true solution and find the minimum, that is the actual true solution. We can never overshoot. It's kind of convenient because it says, even if I mess up these gates, I screw up my estimate of the gap and everything, I'm still guaranteed to get an upper bound. And if I perturb the system and get a smaller number, that's still guaranteed to be a viable solution, okay? And this type of thinking brought about arguably the most famous combinatorial optimization algorithm for quantum computers that I suspect also many of you have heard about, the quantum approximate optimization algorithm, QOA, but by Farhi et al. In 2014, where they said, you know what, take these circuits to be from your problem Hamiltonian, which is now a classical combinatorial optimization, and these parameters here, optimize over them. You know, prepare the state, measure the expectation value, see what you get, compute numerical, I don't know how, compute the gradients, go back and optimize, and when you do optimize, you'll get a good solution, a good approximation of the optimum, right? And it caused a lot of fuss. It was a very exciting thing for a couple of reasons. It was a variational method. It solved combinatorial optimization problems very natively, which was kind of nice. In principle, I could fix the depth beforehand. That's a new thing. Like my algorithm allows me to fit to the device that I have and do the best you can. It wasn't like, if you don't do the best, it just completely fails. No, it still does something, and maybe it's not too bad. We knew that in the limit of infinite depth is correct. It's going to give you the exact solution. That's because of the adiabatic arguments from before. It could minimally use quantum computer. And initially, they had very cool, strong results from theory, which I'm going to share with you again on the slides. In the very first paper, they showed for the max cut problem, it achieves already at depth 1, a guaranteed approximation ratio of 0.684 something, which is not the best one that we have. The NP hard bound is much higher than that, and the relaxation bound is higher than that. But for those who know the history of max cut, it turns out that it took us something like 30 years to go above 0.5. And here already at depth 1, the algorithm did way, way better than that. So this was kind of interesting. Maybe this should be an approximation algorithm, not just an optimization algorithm. And then very, very quickly thereafter, also 2014, December, they studied another problem, which was a constraint satisfaction problem over mod 2 Boolean equations. They got the best approximation ratio known for this problem. And this record stood exactly 4 weeks before Boaz Barak and his guys was kind of, I think they were kind of inspired by this, and they looked into the problem a bit more seriously and actually saturated the NP hard bound. So the quantum record held very, very shortly. But you know, it excited classical people, very serious classical people, to think about this because we had a record of a kind. So yeah, so this is how it started and how it's now going. Well, just a few years later, we started understanding the limitations of the algorithm. So people were mostly focused on d-regular graphs from XCut at constant depth, which is interesting for near-term quantum computers. And there we kind of quickly understood that it can never be better than the GW, Gauman-Williamson SDP relaxation bound in terms of approximation ratios. This was kind of disappointing, but it was also understood why it fails. It fails because of a certain notion of locality of the algorithm. And in the same paper who identified this problem, they actually proposed a fix. They defined something called recursive QoA, which somehow shrinks the size of the problem iteratively and uses QoA at each stage to decide how to shrink it, which doesn't explicitly have the locality problem. And this algorithm is kind of really defeating QoA on these instances where it fails very, very strongly, and everywhere else. It's very efficient. We studied as well with Thomas and Hao Wang and others. We found when it fails, we kind of characterized scenarios where it fails and used some reinforcement learning to improve upon that. So it's a little bit of an advertisement of what we did. This is where I touch optimization time and again, just a little bit here. But somehow this RQA, I will say this again, it is not studied enough, in my opinion. I would like people to think about it a little bit more. But QoA people still think about a lot. It's still being widely studied. The jury is really very much out. Sort of the more hardcore groups are now thinking about highly connected graphs where this locality problem is not an issue. The Sherrington-Kirkpatrick model, which has sort of this random plus minus weights on graphs. And there are now cases where you do beat the best known algorithms, classical algorithms in terms of approximation ratio numerically. We don't really have proofs for these things yet. Benchmarking in terms of, if you forget about the theory part, like does it do better than simulate annealing? I think this is sort of the bane of quantum computing at the moment. It's been so overhyped that people expect results, right? For 10 years, people have been expecting us to do something. We were always saying, well, we don't really have a big enough device, and this is sadly still true. And benchmarks are inconclusive, and I will whine about that a little bit later. So yeah, the jury is still out, but it's still quite exciting, and these are very recent papers like 2025 and so on. And I'm confused why RQA is not studied more. Okay, now I'm going to switch gears a little bit, go beyond QoA and beyond combinatorial optimization, which QoA was defined for, by thinking about it even more generally, right? So we had this picture here. There was a sequence of gates, which the adiabatic theory told me which these gates are, but there was some parameter they could mess around with, one per layer. So it was independent from the qubit number, but it depended on the depth. But you know, it has a logic. It's clever, but you can be less clever. You can say, well, you know, all it does is it prepares a quantum state. That's all it does. And then I measure the quantum state many times, and I measure this expectation value, which ends up being an upper bound on the smallest eigenvalue, right? So what if I prepare some other state using some other circuit and some other state? You can do that. This is what we now call variational quantum algorithms, where the essence of a quantum computer is to prepare some quantum state using some parameterized gates. I told you about this before. And then you measure them, and whatever this does is compute some quantity, which depends on the parameters you used, okay? So it's some function of theta. You can ask me why it's an index here, because I want to talk about something else and I didn't fix it. Yeah, so you can do this. So now, what did we really do? The state space is 2 to the n dimensional, okay? This circuit here that cannot reach all states. What it's doing is it's carving out some hypersurface in this space, something that should be a manifold, but it turns out it's not for technical reasons. And I'm parameterizing it, and I'm trying to minimize on that manifold, right? It's not flat. It's a very complicated thing which does stretch through these exponential dimensions. You cannot really put it in some smaller dimensional space in general, okay? So it's a weird thing, classically hard to capture. And all I'm doing here is it's proposing a solution, which is this quantum state, and then I'm evaluating the quality. That's all I'm doing. And this generalizes QoA, right? You can do it systematically, but carefully changing the ansatzes in such a way as to, for instance, introduce constraints to your optimization to go from unconstrained to constrained optimization. Or you can go wild and say, well, I don't know, I can do these gates, right? And then analyze what happens. Yeah, so now very quickly, just one more technicality that I hinted to, because it's going to be important in some seconds. This thing here, right, this function of theta, it's a real number. right? Recall what I'm doing is I'm getting out an eigenvalue. Eigenvalues are real numbers because these are Hermitian matrices, even though they're complex valued, the eigenvalues are real. It's not an integer, it's not a fraction, it's not a decimal number. How do I get that out of a system, right? So this, now I'm kind of going back to what do I mean by quantum measurement, which I didn't tell you. One thing that you can do with a quantum computer is if you prepare this quantum state, which is this linear combination of bit strings, I can ask it, which bit string are you? And the quantum state wants to tell me I'm none of them because I'm in superposition, I told you already. But you can insist and it's going to tell you which bit string it is. It's going to return a bit string with some probability. And this probability is given by the norm squared of this quantity. So these things here are kind of like quantum probabilities. And all of this exponential stuff, this all looks weird, unless you think about it from a probabilistic point of view, where probabilistic systems, if I have n bits, but it's a randomized system, full description is the probability distribution over this thing, which is a probability for each configuration. There's 2 to the n real numbers that you have to specify, subject to norm 1 normalization. They add up to 1 and they're non-negative. This is very similar, just the norm isn't norm 1, it's norm 2. It's in the Euclidean space. Yeah, that's the difference between quantum mechanics and classical mechanics, pretty much. So I can measure, which means I get a bit string with some probability. Now each bit string corresponds to a possible eigenvalue of this thing. And if my quantum state isn't in one of the eigenvalues, it isn't in one of the eigenvectors, I'll get different bit strings with different frequencies, and I'll add them up, average the expectation value, and I'll get a quantity. Critically, I never get it exactly. I get an estimate. I get an estimate with 1 over, central limit theorem. I'm approaching it, but I'm not there. And it turns out that no matter what I do, this thing which we call shot noise is inherent. Like if I have an algorithm where I want the quantity, which is mathematical expectation value, and I want to quantify the runtime with respect to the error, it's going to be something like 1 over error to maybe some power. And if I'm really, really lucky, the power is 1/2, so I get square root, but it doesn't have to be the case. Classically, if you're dealing with binary approximation of numbers and forget about finite precision, you can get away with things like log 1 over the error. This simply doesn't happen in our case. And you might want to be clever about it. Turns out this is unavoidable and fundamental. And if you could get log 1 over error quantumly, then quantum computers will be space powerful and so on. So it's really, it's not we're not smart enough. We have to live with this, right? Okay, so that was a caveat. Now going back to what are we doing here, I'm optimizing these parameters and estimating this quantity here, and I'm trying to minimize it. If M is diagonal, I said this ends up being combinatorial optimization. If M is a chemical Hamiltonian, you're looking for ground states of molecules, you can use this to compute reaction rates and do things like this. 99.9% of the time, it's not necessary. There are classical ways of doing it. If M is model on a lattice, then you can do funky things. You can study things which are really, really quantum, and we really don't know how to do classically. So it's all in the same framework, right? It's very powerful machinery, which in principle you can run on a machine, which we can build, which we have built, and people have done it. Yeah. All you have to do is this, put parameters, prepare state, and then optimize some quantum function where your cost function is of this form, and it's tailored to solve whatever problem you care about, like is it optimization or not. All you have to do is optimize these parameters. So it's a classical optimization, right? Which is using a quantum black box to give you the value. Later, I'll tell you it also gives you the gradients if you're nice about it. But you have to optimize it. And then how difficult is to optimize this thing? So I'll tell you the good, the bad, and the ugly about how difficult to optimize this is. In fact, I'll tell you the good, then the visually ugly, and not everybody agrees, and I'll tell you a lot of bad, and I'll tell you some silver lining at the end. Are there any questions? Yes?
Basically, you have algorithms that operate over iterations, right? So you have some kind of state and iterate like that, and similar in this algorithm. But it seems to be the case that you have some transformations of quantum state, then you do a measurement, and then you iterate it again. You have quantum algorithms where you do iterations and staying within a quantum state without doing measurement.
Extremely difficult question. Thank you very much. Just to repeat, because I think the recording doesn't capture. So the point was here that it seems to me that I always measure the state destroyed and I have to redo it when I'm doing optimization. Where in the classical world, you know, you take a step, you're in a new state, you move from that state, and then you're in a new state, you don't go back all the way to the beginning. There are ideas where you kind of measure along the way. The problem in the quantum case that, you know, you cannot have your cake and eat it too. You can have a new state, but you don't get to know what it is. If you measure it, you destroy the state, and this is unavoidable. There's things called weak measurements. You can measure parts of it, get some partial information. But in that sense, it's very different. Like getting these trajectories without repeating the entire thing is very rarely possible. And sometimes the fundamental reason why quantum algorithms are not too powerful. So I cannot give you a simple answer. I can give you examples where you can do something that looks like a classical process, but there is a fundamental reason why we cannot simply start where we started, modify the state, and keep going. You cannot measure, go back to the state you were, move forward. If we could, it would be ridiculously powerful, what quantum computers do. Does this? Yeah.
Yeah, the idea was not measure, just keep on updating the quantum state.
What gives you signal where to go? And this is sort of the problem. The moment you extract classical information of the system, it perturbs the state. That's the rock and hard place, right? Or rather the catch-22, not the rock and hard place. I'll have a rock and hard place in a second. Yeah, so it was, thank you for the question. I would encourage more. So the good part is there's something called the parameter shift rule. Maybe one step back. So I'm worried about, I'm doing optimization. It's optimization continuous space. Maybe for you guys, it's not the obvious thing, but for many other people, the obvious thing would be, can we get the gradients out, right? To do some sort of a gradient descent in that continuous space. The answer could be, well, at least you can do numerical gradients. It turns out for quantum computers, that's a terrible idea because the system is highly unstable. And if you perturb the parameter by a little bit, what happens in the end is uncontrollable and you're dead, right? But there's something called parameter shift rule, which is a theorem, which tells you that you can analytically express gradients by a small linear combination of circuits with macroscopically different parameters. You shift them by pi half or pi quarter, so big change, as big as you can make it, and still a linear combination of these quantities is analytically the gradient, right? So at least the obvious killer of computing the gradients is not there. We can compute them, so this was very, very kind of encouraging. We said gradient-based methods are feasible. In the sense, we can estimate the gradients. And that's true. We can estimate the gradients. Gradients of what? What is the loss landscape? According to experts, they're terrible. I'm told this is a technical term. This is an actual illustration of one of them. By terrible, they're highly non-convex. They have provably many, many more local minima, which are terrible compared to global minima, and they're a total mess. They're swamped with traps. There's a paper on them being swamped in traps. You can look it up. It's very interesting. And many of these things are provable. But maybe the most famous problem that we had there is a phenomenon that has been encountered in neural networks before. They call them vanishing gradients. In our community, it's called barren plateaus, which is an asymptotic statement that your ansatz, your circuit, in some structural parameter like number of qubits or depth, has the property that the variance of the loss or variance of the derivative of the loss vanishes faster than any polynomial. So it's exponentially decaying, getting close to zero as you're increasing your system. And this is something you can prove for almost everything that people have thought about so far. As you scale it up, you can compute the gradients to polynomial precision, remember, because I'm doing shots. I'm bounded to polynomial precision, but the quantity of the gradients is exponentially small. So I'm dead, right? So the conclusion was, for all of these cases, by the way, there are other phenomena called value concentration. Turns out they're all the same. Very generic circuits, this was the conclusion of the community. I'm actually going to argue this is not true, but the community concludes they're not optimizable. You cannot optimize them. Emphasizing asymptotical. This is an asymptotic characterization, right? But this is for generic. So then people thought about, well, what if it's not generic? What if I'm a little bit more careful in the design? And if you're a little more careful, you can analyze the circuit and compute something which is called the dynamically algebra of the thing. It's not an easy computation to do, but in principle, you can brute force it even in mathematics if you wished. And people have proven that the variance of the derivative of the cost function, so the gradients, scale is 1 over something polynomial in this dimension. it's big O, but in fact, most of the time is also theta. So it's also lower bounding the thing most of the time. So if this quantity is not that bad, if this dynamical algebra is not exponential, if we have signal, right? The thing is alive. But this DLA, this dynamical algebra, was very cool. People were thinking about it, and they realized, you know how cool it is? It's so cool that if this dynamical algebra is not exponential, I can classically compute what the circuit does. I can simulate it. And this really puts the entire premise between a rock and a hard place, because I need this thing to be small to be able to get gradients. But if it is small, then I don't need a quantum computer to start with. So I'm doing, quantum-inspired methods, which might be interesting, but not what we're in this for. So this was the situation, and then many of my colleagues then set out to write this. The community is a whiplash community. They're like continuously changing, dramatic, and nobody's like sitting. Let's come down. So this paper came out. We need to rethink variational quantum computing because you get to choose whether you're classically simulable or non-trainable, and none of them are good. So this is sort of what this paper said. If you look at anyway, if you look at Marco's Twitter, he's like, I can dequantize this, prove me wrong. That's his meme that is continuously showing. So they put out this paper. Now, at the time, I was aware of this. I was not super worried because as I said, I'm more in quantum machine learning, and somehow we were proving separations. So we were like, why are you guys proving that it cannot be? So we thought about it. We were thinking about, is it really the end for the entire story? But let's slow down. Let's do the slowdown. Go back to what I told you before. What are we doing all along, right? We're taking an optimization problem, in this case, combinatorial optimization problem like max-cut or something like this, right? And then we're turning it into another optimization problem, which is now continuous. The finding of the optimal parameters which minimize this and other thing, right? So it's a reduction. It's a quantum reduction. It's fancy and interesting. And we've just seen that if we do it generically, we take a hard problem and turn it into an impossible problem. It's not good. But it's also not surprising, because the way we're doing it, it had to be. Because all that quantum reductions give us is the power of BQP, because we're combining with classical methods. I don't get to go outside of BQP. And if this worked generically, if I could optimize these things, I can solve NP. I can solve stuff which is, TFNP as well. I should not be expecting this all along. So it had to fail, right? Now, maybe not this dramatically, but it absolutely had to fail. So that's fine. And in fact, whenever it doesn't really fail dramatically, then it's extremely surprising. This is like, why do deep neural networks work when you know you're never close to global optimum? Like, why? We don't know. The community thinks it's strange. It's not something you should be expecting, and the quantum community should have also been expecting problems, right? That's what I'm trying to say. But at the same time, I tried to convince you at the very beginning that there should be stuff that quantum computers do better. So if I have this, then it seems to be like, is it really the variational method itself that necessarily somehow fails? Or are we doing something a little bit too much rush? And I would argue that the answer is, with quantum computing, it's always fine print. It's like working with banks and lawyers. I take it back. I don't want to be sued, and this is recorded. It's like it's never, ever, ever, ever that easy. Like when there's a theorem, if a theorem is this long, if you write another theorem which is this long, it's incorrect. Like it really has to have all the epsilon and deltas inside for it to be true. And sometimes it really matters. And there's fine print in here in the sense of how they're averaging over the outcomes. But for us, there was like this intuition that we talked about parameters quantum circuits. Yeah, sure, but I mean, I can think of parameters being of two different species, and I call one inputs, the other ones are parameters. Like you can think of neural networks where I put in, a one, but I treat the weights at the input as an input. So now the neural network doesn't have an input, just has weights, but the first layer of weights is the actual input, right? But it's just weights. So I do the same thing here. So now I'm representing a function, and I can make it such that it's universal for quantum computing, and these results would somehow have a consequence that I can simulate that, right? But because I can make these parameters vanish, like not be important at all. Something had to give. There was something was a little bit too general, but with big consequences. It's not that obvious. One would have to be careful about. I just want to highlight that the paper is absolutely morally true. In some sense, all quantum circuits, well, majority of quantum circuits are classically simulable. What I mean by this is if you randomly start putting quantum gates on a circuit, and you measure an expectation value, you will see 0 with exponential large probability. This is also true for classical circuits. Like the closest formal statement that I'm happy to say is like if you randomly pull a Boolean function out of a set of Boolean functions, and you ask what is the fraction of inputs on which it becomes 0 or 1, it's 50-50 with overwhelming probability, right? So you never see signal, because in the quantum case, all I do is estimate expectation values, but they're always the same. They're 50-50. Not always. Exponential fraction of circuits has this property, but also an exponential large fraction of circuits doesn't have this property, and this is where quantum computing lives, and this was asking too much, right? And you can make it formal. So this is our paper, which kind of came out almost at the same time as this one, but we had a different statement. We kind of said, no, it's not dead. There is room in between. You just have to be careful. So these are the contexts, like gradient-based trainability, absence of barren plateaus, whether you can dequantize it and whether it can be simulated, which is not really the same. And we kind of proved that no implications follow, right? Nothing implies nothing directly. Everything has fine print, right? And in fact, you can have things which are simulable, but trainable and variational. All of these things are possible if you're careful in the design. So the statement is, we were too generic still. We have to be more clever in the design of the circuit. Now, I'm totally out of time. So I just want to tell you that, well, I didn't want to be clever. What did I want, right? I wanted something else. I didn't know how to program a quantum computer, so I built a circuit and asked you guys to optimize it for me. I don't want to think about it. That's what I want you to do, right? And now these guys tell me you ain't gonna have it. Look, I don't want to think. I want other people to think. So theory says this will not work generically nor asymptotically. And again, this is something everybody knows. Like nobody would expect that. What I needed is to work for useful sizes, right? And in some cases, it makes sense. And this, for me, is still wide open. And this is where the synergy between quantum computing and optimization becomes really, really strong. Maybe you have barren plateaus. What does that mean? Asymptotically, they vanish exponentially quickly. Yeah, but how big are they for 10,000 qubits? What's the number? And as long as this number, 1 over gradient, is much bigger than classical compute time, you can have an advantage. It's fine. It's not an asymptotic advantage. It's wall clock time that we can talk about beating, right? And this, for me, still motivates very much working further on classical optimization methods for these landscapes, which are nasty and difficult and not like something you encounter regularly, but still something that has structure. And Hao Wang is in particular pursuing this quite a bit. So this is one of the references of the papers we did together, just for reference. And in fact, I mean, given successes in AI in general in recent times, I would expect AI to do more for me. I wanted not just to optimize the circuits, I want to tell me what the right circuit is. So this is something we also explored with reinforcement learning, where an agent creates a circuit which is designed to solve some problem, either optimization or, in fact, we did mostly chemistry and some physics. And it turns out it does find circuits which are better than anything we know from theory, right? It scales. It's not an algorithm, right? It's a fixed size thing. It beats everything we know, right? It doesn't scale up, right? So we need better optimization, better AI for this. And that's an open challenge for all communities. And now just to end with a little bit of tongue in cheek, I just wait for somebody to say, aha, so we have a quantum algorithm for a classical problem and then a classical algorithm to optimize this thing. Why not put a quantum algorithm to optimize this thing? And then we have quantum inception. And I'm sure somebody's going to try to chain it further and further and further, and it might make sense. I'm not entirely sure this is a totally crazy idea. So just some final thoughts, just going back to the very first question that I didn't really ask as the main question, but it is whether quantum computers can help in optimization. You have to be aware that when people say quantum computers, they can mean one of at least 3 different things, like the thing we can do now, the thing we can do in the first generation of fault tolerance, or the thing that is assumed in Nielsen and Chuang's book from the early 2000s. And we don't know when we're going to build this, and you get 3 different answers, right? But even the most pessimistic case, I think the majority of the theoreticians in quantum computing are very skeptical about optimization. Here's a counter argument. We've managed to kill a lot of stuff in quantum computing. We managed to be very sure that it's not going to tackle NP in general. We've killed completely generic improvements for exponential improvements for machine learning. We're really working hard to kill quantum computing. Like the community really doesn't like itself in a way, at least parts of it. And yet optimization survives. And yet every year there come out new ideas how to solve problems that are not broken, and even the old ones are not entirely broken. And one of them that is very exciting is called decoded quantum interferometry. I don't have time to talk about it, but here's a reference for you. I can send you the slides, which has the really, really strange property that you can classically compare the performance of the classical and quantum algorithm without actually being able to run it. It's something that we can definitely do with respect to some metrics for generative models. That's something we work on quite a bit. For me, it's revolutionary because I can tell you something about how good your quantum computer is going to perform once you have it without the power to run it. For generative modeling, I can explain easily why this is not impossible. For this, I don't fully understand, or I forgot, I'm not sure why this is possible, but that's very exciting because now we can actually do the one thing that really matters, and that's actually benchmark. So that's sort of the future. Quantum machine learning exists, it's cool. We can do a lot of things better than classical computers. And these are the people who are involved in some of the work that I talked about. We're Applied Quantum Algorithms Group, and we like talking to people from all fields. So feel free to talk to us. Thank you.